Hello students. So today's video session we will be mostly covering one of the dimensionality reduction technique, which is the most prominent one, called as principal component analysis or PCA. So before understanding what do you mean by principal component analysis, let us see why or what is the need for PCA. So if you see this particular figure, you can see it is written curves of dimensionality. So the first figure is nothing but a one-dimensional space where there is a coin that is lost over a line which is of 100 yards. So for a man to find this lost coin over a line of 100 yards is easy. But if we consider a square which is of size 100 yards, then the effort and the time required by the man to search that coin will be more as compared to case 1. And still if we go further and we consider a cube, that is the three-dimensional space, then the time taken is going to be all the more for the person to find the coin. So from this figure, it can be interpreted that higher is the dimension, the complexity increases proportionately. So the need for PCA: high dimensional data is extremely complex to process due to inconsistencies in the features, which increase the computation time and make data processing and EDA more convoluted. Convoluted means complex. So if you have got a data set and there are multiple features, it will increase the complexity and the computation time. So it is very important the features which are not contributing to the training of the model, they should be removed so that the model can be trained appropriately and in less time. That is, simply reduce those features. That is why the name dimensionality reduction. So from a high dimension, we move to a low dimension. Now, what is principal component analysis? Principal component analysis is a dimensionality reduction technique that enables an individual to identify correlations and patterns in a data set so that it can be transformed into a set of significantly lower dimension without loss of any important information. So what does this definition imply? You have got a data set which includes multiple features. It is essential that we remove those features which are redundant, unnecessary, and highly correlated. These are the three key terms. Remove inconsistencies in your data or information, remove redundant data, and remove highly correlated features. Highly correlated features are nothing but those features that provide a biased output. So if such features are there, then there is a possibility of providing a biased output. We must consider those features which are independent of each other. We do not want dependent features. Otherwise, what will happen? We will be getting a biased output. Our model will be trained in a biased manner. So if you check over here, if you have got your original data containing approximately 5 columns, then by applying dimensionality reduction, we are getting 3 columns, and the result which is provided by the new data set should remain the same that it will be provided by the original data set. That is why the emphasis is on the term without loss of any important information. So new data space with lesser features that retain most of the information. Now let us see what are the different steps that are followed to apply principal component analysis. The first step is standardization of the data. Second step is computing the covariance matrix. Third one is calculating eigenvectors and eigenvalues. Second last one is computing the principal components. And finally, we reduce the dimensions of the data. So let us understand each of these steps in depth. So the first step is standardization of the data. Standardization is all about scaling the data in such a way that all the variables and their values, they lie within a similar range. So if I'm considering this particular example, rating feature lies in the range of 0 to 5, whereas number of downloads feature lies in the range of 100 to 5000. So if I'm using this data as it is, then this particular feature, that is number of downloads, becomes more dominant as compared to the rating feature, because the range of this particular feature is comparatively larger as compared to that of the rating feature. So it will provide a biased output, and we are not interested in training our model in a biased manner. That is why data standardization is essential. So the formula to calculate is variable value. That is, if I want to perform the standardization of this particular column, first I will calculate the mean. And once I obtain the mean, what I'm going to do is variable value. So 1383 minus the mean of this particular column divided by the standard deviation. So here in this case we have got 5 rows. So the total number of rows minus 1. So it will be 1383 minus mean divided by 4. 5 minus 1. So this is the first step. Now the second step of principal component analysis is computing the covariance matrix. A covariance matrix expresses the correlation between the different variables in the data set. Variables are nothing but features, as we saw over here, the relationship between different features. It is essential to identify heavily dependent variables because they contain biased and redundant information which reduces the overall performance of the model. So here in this case, if I had got multiple columns, and out of that if number of downloads was highly prominent or dominant, so in that case what would happen? We would have received a biased output. So this is your covariance matrix for your two features. So if I'm considering two features over here, then it is covariance of A comma A, covariance of A comma B, covariance of B comma A, and covariance of B comma B, which is a 2 cross 2 matrix. And this matrix denotes how codependent two variables are. So if you are getting a negative value of covariance, it indicates that the variables are indirectly proportional, and if you are getting a positive value of covariance, it indicates that they are directly proportional. Now once the covariance matrix is obtained, we have to calculate the eigenvalues and the respective eigenvectors. Eigenvalues and eigenvectors are the mathematical constructs that must be computed from the covariance matrix to determine the principal components of the data set. So, once the covariance matrix is obtained, we need to calculate eigenvalues and eigenmatrix vectors. So, eigenvectors are those vectors when a linear transformation is performed on them, then their direction does not change. Eigenvalues simply denote the scalars of the respective eigenvectors. To understand these statements, in the upcoming video, we will be taking a numerical. So principal components are the new set of variables that are combined from the initial set of variables. They compress and possess most of the useful information that was scattered among the initial variables. So initially, if we had got 10 variables, by performing principal component analysis, we are coming to a conclusion of only 3 variables. So what is happening? The output that you are receiving remains the same. So a model with 3 features or variables is preferable as compared to a model with 10 features because there is no loss of information. So once the eigenvalues and eigenvectors are obtained, we have to compute the principal components. So all we have to do is order them, that is the eigenvalues and eigenvectors in descending order, where the eigenvector with the highest eigenvalue is the most significant and thus forms the first principal component. So if I am having, for example, 5 features, out of that I found out the covariance matrix and the eigenvalues and eigenvectors. And from there I found the values and I then arranged those eigenvalues and eigenvectors in descending order. The one which has got the highest value will be the first principal component. Then the second one in the descending order will be the second principal component. So the first principal component that is obtained is the most significant and stores maximum possible information. Principal component 2 is second most significant component and stores the remaining maximum information and so on. So arranging the eigenvalues and eigenvectors in descending order will help us in obtaining principal component 1, principal component 2, where principal component 1 contains maximum information which is essential for training the model in a particular data set. And PC2 will contain the remaining information, so on and so forth, depending upon how many features we have considered in our data set. So the last step is reducing the dimensions of the data set. So this was our original data. By applying principal component analysis, we have reduced our data, and this data we will be using for training our machine learning models. So the last step is to rearrange the original data with the final principal components which represent the maximum and the most significant information of the data set. So if you check over here, we have movie ID, title, genre, user ID, movie ID, rating, timestamp. So maybe after applying principal component, we come to a conclusion that your principal component 1 would be your movie ID and your user ID, and then principal component 2 would be your movie ID, principal component 3 would be your rating ID, and finally the timestamp. The redundant columns like genre has been removed as well as title is removed. So we can perform, this is a data set that is given for movie rating data set that contains the ratings from 700 users for approximately 9,000 movies. So you can try this particular implementation of principal component analysis in Python. So to perform step-by-step principal component analysis on movie review dataset in order to reduce the dimensions of the data. So first we perform standardization of the data, then we calculate the covariance matrix, generate the eigenvalues and the eigenvectors, arrange them in descending order, and finally obtain the principal components. University questions. Describe the steps to reduce dimensionality using principal component analysis method by clearly stating mathematical formulas. Describe how principal component analysis is carried out to reduce dimensionality of datasets. Thank you.